Frames of reference by Augmented Newtonian dynamics. In Einsteinian physics, the concept of a frame of reference plays a vital role. But what exactly does this term signify? A frame of reference is the chosen standpoint from which the motion of bodies is described and measured. It provides a fixed origin and set of directions relative to which positions, distances, velocities, and times are defined. Different observers may adopt different frames, but within any one frame the laws of motion apply consistently and yield a coherent description of events. The first consistent treatment of frames of reference was given by Galileo Galilei, the great Italian polymath. His transformations, later adopted into Newtonian physics, are familiar to all of us. For instance, consider two cars, A and B. Car A is moving at 50 km per hour, and car B at 80 km per hour. If both are moving in the same direction, then car B is said to overtake car A at a relative speed of 30 km per hour. Similarly, if the cars are approaching one another, they are closing the gap at a combined rate of 130 km per hour. This simple addition and subtraction of velocities is the essence of the Galilean transformation, and it corresponds with our daily experience. But now imagine we are not dealing with solid cars but with waves. In this case, Galilean transformations do not apply, because a wave maintains its own speed regardless of the motion of surrounding objects. The difference between the two systems is that while cars, obeying Galilean transformations, can overtake one another by traveling at different speeds, waves in the same medium all propagate at the same characteristic speed. For waves of a given type in a given medium, different speeds do not exist. They cannot overtake, they can only superpose and travel together. For centuries, the understanding of nature rested on the foundations laid by Isaac Newton. In his conception, space and time were absolute, reliable coordinates by which all motion could be measured. Time flowed evenly, and was the same for everyone. Space provided a fixed framework, a reference against which events could be described. Within this vision, motion was orderly. A body at rest remained at rest, a body in motion continued in a straight line unless acted upon by a force. These were Newton's inertial frames of reference, and they gave science a clarity that endured for more than 400 years. Mass, in Newton's universe, was also constant, unchanging, the measure of matter itself. This framework was not only elegant but profoundly successful. It enabled astronomy, engineering, and physics to advance with unmatched confidence. Yet, at the dawn of the 20th century, experiments with light began to reveal limits to this system. And it was then that Einstein advanced a new way of thinking, reshaping our understanding of space, time, and motion itself. Einstein attempted to show that the speed of light is the same for all observers, regardless of their motion. From this bold starting point, he reconstructed the very concepts of space and time. In Newton's universe, space was fixed and time universal. But Einstein argued that both are relative. The flow of time depends on motion. The measure of length changes with speed. Even the notion of simultaneity, two events happening at the same time, becomes dependent on the observer's frame of reference. In this vision, no standpoint is privileged. Each observer, whether moving swiftly or standing still, carries their own coordinate system, their own clock, their own measure of distance. The laws of physics hold equally in all. Mass, too, was drawn into this relativity. A moving body carries more energy, and energy itself is linked to mass in the famous relation E equals mc squared. What Newton had treated as fixed, Einstein attempted to reveal as dynamic, interwoven with the fabric of spacetime. Thus frames of reference were recast, not anchored to absolute space and universal time, but to a spacetime that bends and shifts with motion. Newton's framework remained powerful for everyday experience, but Einstein's theory sought to address the behavior of light, high velocities, and the cosmos as a whole. Imagine two friends meeting in a cafe in Paris. They agreed to meet again, in the same place, at the same time, 1 week later. Simple enough, or so it seems. But in that week the Earth has not stood still. It has spun on its axis, turning at more than 1,600 km an hour at the equator. It has raced around the Sun at nearly 30 km per second, about 108,000 km every hour. And the solar system itself is hurtling through the galaxy at 828,000 kilometers per hour. Even the galaxy is not fixed. The Milky Way is moving through the universe at roughly 2 million kilometers per hour relative to the cosmic background. So when the friends meet again the following week, it is only in a local sense that they are in the same place. From a cosmic perspective, they are billions of kilometers from where they first met. This is where Einstein's insight comes alive. He attempted to show that there is nothing absolutely fixed in space. Motion, position, even the measure of time itself, all depend on the frame of reference. Locally, we can speak of the same cafe, the same hour. But in the wider sense revealed by modern astronomy, such certainties dissolve. Space and time are not absolutes, they shift with perspective. Sir James Jeans once compared frames of reference to a handkerchief thrown into the sea, drifting and folding with every wave. But imagine trying to mark the position of such a handkerchief. Without a fixed shore, without an unmoving backdrop, the very idea of where becomes meaningless. This was the challenge Einstein brought to physics. By denying absolute space and absolute time, he stripped away the foundations on which Newton had built. Newton's laws were not simply adjusted, they were torn apart. The entire framework, absolute space, universal time, constant mass, collapsed when measured against a reality in which nothing is fixed. This was not evolution but revolution. Newton's majestic system, which had governed physics for centuries, was rendered irrelevant. Like a map drawn for a world that no longer exists, it could no longer describe reality. A new order had to be built from the ground up, and Einstein claimed to provide it. Imagine a boy on a moving train. He throws a ball straight up into the air and catches it again. Simple enough. Now ask, what does an observer standing on the platform see? Einstein would have it that the platform observer sees the ball travel in a parabola, tracing out a longer path in the same time frame. But in reality this does not happen. The ball acquires the same forward momentum as the train. While it rises and falls, it maintains that momentum. To the boy on the train, it moves straight up and down. To the observer on the platform, it also moves straight up and down, in step with the train. Both see the same reality, there is no slanting path. With a photon, however, the situation is different. A photon has no mass. It cannot be carried forward by the train's momentum in the way the ball can. And so we come to Einstein's photon clock experiment, a light beam bouncing between two mirrors on the ceiling and the floor of the train. What, then, does the platform observer really see? Now consider a photon clock on a moving train. The source of the light sits on a mirror on the floor, another mirror is fixed 3 meters directly above it. One tick of the clock in the stationary train is a pulse going up 3m and back down 3m, 6m total. At light speed, that tick lasts 20 nanoseconds. Einstein would say, to the boy on the train the pulse goes straight up and straight down. But for the observer on the platform, because the train is moving, the pulse must trace a diagonal to catch the mirror, so the path is longer, the tick is longer, and time must run slow. What really happens is simpler. The speed of light is constant, the motion of the train does not affect it and it does not acquire the train's momentum. Take a modest train speed, 20 meters per second, almost equal to 72 kilometers per hour. In the 20 nanoseconds of one tick, the train moves only 20 meters per second times 20 nanoseconds equals 0.4 micrometers forward. Both the boy and the observer register the same action. They both observe light moving the same distance in the same time. Nothing changes. There is no need to stretch time or shrink length to keep light speed constant. The clock's dimensions, 3m up, 3m down, its tick, 20 nanoseconds, and the train's minute forward shift, 0.4 micrometers per tick, leave no paradox to solve, no time dilation, no length contraction. Both the boy on the train and the observer on the platform see the same thing. Now consider another implication of special relativity. Imagine two stars, separated by 4 light years. Between them, 5 spaceships set out together, each at a different fraction of the speed of light. Spaceship F travels at 0.3 c. Spaceship G travels at 0.4 c. Spaceship H travels at 0.5 c. Spaceship I travels at 0.6 c. And Spaceship J travels at 0.7 c. According to special relativity, each ship does not merely take a different time to cross the distance. For each ship, the distance itself is different. The faster the speed, the more the distance contracts, the more the clock slows. So the 4 light-years between the stars are no longer a single, objective span. They become 5 different spans, 5 different durations, 5 different realities, one for each ship. But how can this be? The 2 stars are where they are. They are separated by a single, definite distance. Yet relativity insists the space between them fractures into multiple versions, each tailored to a moving observer. And if this is true for just 5 ships, what happens when there are thousands? Millions? The very fabric of space becomes a patchwork of contradictions. Carried to its logical conclusion, this picture makes the universe almost uninhabitable. Life, matter, chemistry, all depend on order, on shared measures of time and distance. But if space and time are forever splintering, how could anything stable ever form? How could atoms bind, molecules endure, or living beings evolve? This is the hidden cost of taking time dilation and length contraction as literal truths. Instead of one coherent cosmos, relativity leaves us with countless fractured ones. In order to make this concept clearer, imagine 2 spaceships leaving Earth at the same moment, bound for a star 4 light-years away. Spaceship A travels at 0.4 c. Spaceship B travels at 0.9 c. Now, according to special relativity, for ship B, in Earth's frame the trip should take 4.44 years, 4 divided by 0.9. But in its own contracted frame the distance is shorter, only 1.74 light-years, so the journey lasts just 1.93 years by its onboard clock. For ship A, in Earth's frame the trip takes 10 years, 4 divided by 0.4. In its contracted frame the distance is 3.66 light-years, so the journey takes 9.15 years by its onboard clock. Now picture the arrangement. Ship B races ahead, drops off cargo at the destination, and returns home. Ship A is meant to arrive later, pick up that cargo, and bring it back. But here's the paradox. When Ship A finally reaches the star after its long voyage, the inhabitants there tell its crew, "What cargo? No ship ever arrived. We never saw Ship B." In Newton's mechanics, the distance is fixed. The star is 4 light-years away, no matter who measures. Every ship covers that same distance, only the travel time changes depending on speed. In relativity, the distance itself is said to shrink for the faster ship. For Ship B at 0.8 c, the star is only 2.4 light-years away. But the star can't simultaneously be both 4 light-years and 2.4 light-years away in the same universe. If it's 2.4 light-years away for B, then the star must be physically closer in his reality, which means they no longer share the same location at all. If 2 observers insist the same star is in different places, then they are not describing one common universe anymore, but 2 mutually exclusive ones. The theory of relativity may be faulty, but the observations remain. We look into the sky and see a universe in constant motion. Planets spin, stars orbit, galaxies drift. There seems to be no fixed stage, no anchor point, no permanent frame of reference against which everything can be measured. Newton gave us a universe of absolutes. Time flowed evenly, space stood still, mass was constant. Einstein, in reaction, denied all absolutes and made every frame relative. But neither vision fully captures what we observe. For in reality, nothing is fixed, and yet, without some reference, how can motion be defined at all? Physicists have long speculated about one possibility, the existence of a universal frame of reference. A hidden backdrop, silent but present, which gives coherence to the whole. Against this frame, time and distance would have meaning. Against this frame, the stars would not splinter into multiple versions. Whether it has been called the aether, the cosmic rest frame, or the field of dark matter that pervades the cosmos, the idea persists. A single reference frame, underlying all others, that restores order to a universe otherwise adrift. More tellingly, there is considerable proof that the aether might not be a myth after all. It may exist in the form of what we now call dark matter. Its origin can be traced back to the Big Bang itself, when an unimaginable flood of light filled the newborn universe. As the cosmos expanded, these photons, trapped within its bounds with nowhere to escape, expanded with it. In doing so, they gradually lost energy, slipping from real photons to virtual photons of vanishingly small energies. These virtual photons never disappeared. They permeate every part of the universe. They form an invisible sea of infinitesimal electric dipoles, a medium that is not static but evolving, changing, transforming, shaping the behavior of matter and energy at every scale. The evidence is striking. Vera Rubin's work on the rotation of galaxies showed that dark matter must account for at least 85% of the universe's mass. Modern studies have raised that figure to nearly 90%. And yet this immense presence is silent. It allows light and every form of electromagnetic radiation to pass through it unhindered. Dark matter may therefore be more than a hidden weight. It may be the living fabric of the cosmos itself, the substance that permits light to travel, that allows energy to be exchanged, and perhaps even the very medium through which gravity is transmitted. In this view, dark matter is not dead residue of the Big Bang. It is the ether reborn, an unseen but ever-active field, evolving, changing, transforming, and giving coherence to a universe in motion. The restoration of an ether into physics does more than revive an old idea. It resolves many of the contradictions left by relativity. It explains how the speed of light can be constant, not by bending time or shrinking space, but by providing a universal medium through which light always moves. Though invisible and ephemeral, this ether restores coherence. Time and space can once again be regarded as constant measures, as Newton imagined, but now grounded in a physical medium that pervades the cosmos. Far from being a step backwards, this is a step beyond. Newton's absolutes and Einstein's relativity both captured part of the truth. The ether, understood today as the sea of dark matter and virtual photons, ties them together. It offers a universal frame of reference, a common backdrop in which events unfold, and a medium through which both light and gravity act. And most telling of all in this new way forward is the possibility that everything, from the stability of atomic structure to the great force of gravity itself, might be explained within this single paradigm. The end.